Today, we are joined by two experts in the cloud. So first of all, I will start with you, JJ. JJ is Cloud Business Development Manager Americas. So JJ is the Global Cloud Business Development Manager at Ansys. He is helping to guide our Ansys customers in their cloud journey. And he has been working on migrating CAE simulation to cloud-based HPC infrastructures for 10 plus years. And he has been with Ansys for 4 plus years now to help guide the cloud strategy and lead the go-to-market efforts. We are also joined today with John Baker. So John is our Cloud Business Development Manager Europe. And John is helping our customers to achieve their product design testing ambition by incorporating powerful and flexible cloud HPC technology into their workflow. John has an impressive background. He's a PhD in computational chemistry from the University of Nottingham with a focus on GPU algorithm for molecular dynamic simulation. He is passionate about HPC technology and workflow with 10 plus years of HPC infrastructure experience. His previous role includes supporting a famous UK racing team for the HPC infrastructure and the UK national supercomputer. So that's impressive. And we are also joined by Asma and Krishna Samavedam in the back end, and we are going to answer your questions. So during this presentation, do not hesitate to ask. We are joined by Krishna, who is our PM, Product Manager. At this time, I will turn the event over to you, JJ.
Thank you so much, Thomas. Appreciate the introduction. As much as you tried, Dr. Baker there always tends to outshine me on his background, which is why we have him on the team. So everybody, thanks for joining our webinar today, Transforming Physics Simulations with Ansys and Microsoft. We're going to start off with an agenda. My slides are not advancing correctly. There we go. Okay, so now that we have the agenda slide. So first we're going to start out with, we understand that there might be a mix of some people on this team, some members of engineering, some members of IT. We want to make sure that we're bringing those two communities together. So we're going to start with a little explanation of what physics simulations are and why they require intensive compute power. We're going to then talk about the challenges faced by engineers because of the compute power required by CAE simulations, how you can leverage the cloud to boost that compute power and the benefits that you will get when accessing the cloud for these simulations. And then I'll be handing it over to Dr. John Baker at that point, and he'll be going over our solution on Microsoft Azure with some nice videos to give you a good demonstration in the limited time we have, a good demonstration of what this solution looks like and how your users can benefit from that. Obviously, we'll end with a Q&A. As Tomas said, please enter your questions as you're going along. We'd be happy. We have multiple members on the call that at any time are not presenting, including Krishna, John, myself. So we will be, and obviously Tomas and Asma, we will be answering questions as we go. So as questions enter your mind, please enter those questions in the chat. And then if we have time at the end, we will cover the questions at the end in a Q&A format. So with that, first thing is, what are physics simulations? So you can see on the screen, we have a number of simulations running in a multi-view here that are showing a variety of post-process physics simulations. And what you're seeing, if we kind of zero in on the center of the screen there, where you're seeing a blue car crash into a barrier. Okay, this is a digital test of what would happen if you crash that car into that barrier. How much would the car deform? Where would it deform? Where would the engine go? How would the occupants respond? And you could see an actual human dummy model that's been loaded into a car seat for a similar crash simulation just above and to the left of that. And there's a wide different variety of examples here. This one is kind of heavily focused on automotive. So you see, fluid in a gearbox and how that fluid is behaving in that gearbox while the gearbox is turning. You see airbag deployment. You see signal integrity for autonomous driving or assisted driving features. All of these are what we call physics-based simulations. That means that the way things behave in the real world are based on the laws and rules of physics. So therefore, with a computer, you could simulate what would happen in the real world. And the whole idea of this is allowing you to do digital testing, because that, going back to that blue car in the center of your screen, it is very expensive to crash it, to build a one-of car and crash it into a wall. Most of the tests that are done nowadays by major OEMs and tier 1, tier 2 suppliers are actually not tests, they're verifications. They know exactly how that car is supposed to deform, or how that impact is supposed to affect the car, and they merely verify it with one test. They're able to do that because of the physics-based simulation software that Ansys offers. We are able to do that because of the laws and rules of physics, and anyone that took physics in high school or college knows that physics involves math. And essentially, that is what we are doing. We are doing a lot of math in order to be able to provide these virtual prototyping and testing of your products before you build a single thing. The problem comes in that the amount of math that we are doing. We are doing an absolutely a massive amount of math for all of these individual simulations to do the solve phase. What you're seeing here is the post-process phase. Once the solve is done and you want to create the images that show you how air is flowing, how fluid is flowing, how things are deforming, that's done in the post-processing stage. In order to get to this, you have to do a solve. And a solve is going to do a lot of math and require a lot of computation. And that's where high-performance compute and cloud computing comes into the picture. So there we go. Finally got the slides to advance correctly. So why is this a problem? Okay. Virtual prototyping offers a lot of enhancements and a lot of cost savings, both in cost to produce physical prototypes, but time to produce physical prototypes. Those are not cheap, and they are not done quickly. When we did we worked with digital engineering to do a study on HPC and cloud computing for engineering simulation, and this went to engineering managers and C-suite. And the top answer for the top business challenge in design activities from all of our respondents to this survey, and there were a massive number of participants, 740 different IT managers, engineers, and C-levels. 54% said their top business challenge is the pressure to reduce design cycle times. That is exactly what Ansys as a company exists for, is to help you simulate with virtual prototyping and reduce your design cycle times to get a better product out faster. That's the number one problem, so that's good. At least good for us, because we helped solve that number one problem for more than half of the users. The other interesting thing from this survey is we are increasingly moving beyond workstation level compute. So we kind of set that cutoff at 12 cores. And 4 years ago we had users that were, or actually 3 years ago, the survey was done last year. 3 years before that, only 44% were using more than 12 cores. Now it's up to 50, and it's climbing. Okay, so more people are using more and more cores in order to get their simulations done, because they're getting more and more complex and they need to get better answers, so they're using more and more cores if they have them, which is an important point. And then we have also increasing is the number of users that their simulation runs take 9 hours or more to solve. So this is what we consider an overnight or a full day run, which means every time you run that simulation, it is a day added to your project cycle. Every single time you run that simulation. 21% in 2020, when we redid the survey last year, 30%. Okay, so that's nearly a 50% increase, and that also is continuing to climb. The bottom line is the demand for compute resources is increasing, and we want to be able to make sure that we are supporting that with our cloud innovations, and that's why we're here talking today about what we're doing on Azure. So when you have access to cloud computing, So we've covered what those simulations are. We've covered the reason for the need for compute. Now to talk about what does it mean when you have access to the cloud. The cloud will give you access to a wide variety of resources, nearly 500 different core types, global availability, and massive scalability. Okay, so what that does, first and foremost, going back to the core thing that I mentioned when I covered what our physics simulations are, is we want to help you get a better product to market faster. By having the cloud, you have the increased flexibility of being able to grab what you want when you need it as far as CPU power or GPU power, and increase your productivity, which at the end of the day will help achieve on that goal, that goal that is, you know, their biggest complex problem, as reported in that survey previously, faster time to market with a better product. Okay. On the note of better product, you will be able to do more in a reduced amount of time, so you can improve the overall quality of your final product. So better product to market faster. And then the key thing that when we built Microsoft Ansys Access on Microsoft Azure is we wanted to streamline the workflow and maximize the cost and efficiency. And so that really brought about the creation of a fairly unique product that we're excited to share with you today. So what is Ansys Access on Microsoft Azure? Well, it goes back to the strategic partnership that we formed with Azure, going back multiple years now, where we wanted to deliver on the most cost-efficient and workflow flexible way for our customers to be able to run Ansys simulations on Microsoft Azure. So what we've done is we've created Ansys Access on Microsoft Azure as a means to deploy Ansys tools in your Azure environment. And that's a key thing. You're going to hear me hit on that a couple of times. That is a key thing, is it allows you to deploy in your Microsoft Azure environment. We will handle the configuration of everything, and we'll cover kind of how that's done in later slides. But this allows you to continue the migration that you have already done on Azure, if you've already done it, or it allows you to open up that opportunity to do what is considered some of the most complex cloud migrations to perform, which is multi-node HPC. This makes that conversion much easier, much more simplified, and allows you to access the power of Ansys software along with the power of Microsoft Azure. To kind of go into the details of what we're deploying here and how we're deploying this. So the first thing that we're doing is we have the Ansys applications pre-configured through an Ansys web page portal. So the way you access Ansys Access on Microsoft Azure is you first log into an external web page. That external web page is your launching pad. From there, you would determine what machines you wanted to run and what you wanted on those machines, and we will have those Ansys applications pre-configured. This isn't just the base installation of Ansys. This is everything that is needed in order to ensure optimal production. You're going to see a lot of benchmarks flashed across the screen in this. This is just an example that we have here. You're going to see a lot of benchmarks, especially as John gets into his portion, that will show you kind of, you know, how we've tested the system and ensured that everything is preloaded, pre-configured, and ready to go. So we ensure that when you're deploying that, you're deploying it with the fastest speed possible. When you're running in the cloud, time is literally money. You pay for every second that you use, so the most efficiency that we can deliver is cost savings returned to you. The other thing that we do is we make it very easy for you to access this. You'll see a demonstration of this later, but this integrates with some Azure services on the back end and some Ansys services that allow this to be a very streamlined dynamic cluster system where you could spin up and spin down resources as you need. These tools are available to end users, things like CycleCloud on Microsoft Azure, but we allow it to be very easily substantiated through a very simple web UI. It is designed so that end user Ansys engineers that are used to running Ansys can configure and deploy their own assets as needed. Now, you may not, IT people might say, I don't know about that. You may not choose to have them to be able to do that, which is why we add in a layer of control on this. So you can see in the screenshot here to the left, these are our permissions and project space settings for end users. So we have the ability to control what users can do. Are they allowed to build their own resources? Or are they allowed only to stop, start, and connect to resources that you build for them? So you have the ability to control that. And then the obvious question is, if we've ensured performance is good, we've made it easy, we've given you the control, what is the cost of this item? Now, we offer further to control, we offer budgeting aspects in this so that you're allowed to set budgets within your different project spaces within the environment. Everybody can be granted access to multiple different project spaces, so they each have their own experience when they log into Ansys Access. But on the costing side of things, this is where it gets really advantageous. There is no cost to onboard to Ansys Access, to set it up or anything like that. There may be some things that you incur on the Azure side, whether setting up VPN connections or creating and storing machines that will cause a charge on the Azure side. The only charge that ever comes in from the Ansys side is we add 25 cents to the VM cost for whatever VM you're running, and that's 25 cents per node. So if you spin up a virtual desktop using the system that is a $3 virtual desktop, it will then cost you $3.25 per hour. Same thing on a multi-node HPC. If it had 10 nodes of something that's $3, then we're going to have the 3 times 10 for the nodes, which would be $30 an hour, and then the additional 25 cents times 10, so an additional 25 cents. So 25 cents is it. It's a very small addition. This is all done through your Azure billing. There is no billing from Ansys on this whatsoever, no POs to Ansys, anything like that. It's a bit of a unique product. It is Ansys built, Ansys maintained, Ansys supported, but you buy it through the Azure Marketplace, and everything is paid for through the Azure Marketplace. So a little unique in what we're doing there. So just to summarize, this system is a way for you to complete not only your Ansys simulations, but all CAD and CAE workflow. We are going to handle the deployment of Ansys applications, but you have the ability to load any applications onto these machines that you want once they exist. So if you wanted to create custom desktops for your users that had, their CAD software, had Office Suite, anything like that, you have the ability to do that, okay? The other thing that it does, and I said I'd reiterate this a couple times, so to reiterate again, this leverages the existing commercial agreements that you have with both Microsoft Azure and with Ansys. So with Azure, you will be leveraging your agreement with Microsoft Azure. These VMs will be spun up in your environment. The portal that you access, the Ansys Access on Microsoft Azure portal, is outside of your environment, but then all it is doing is coordinating. It's coordinating machines, it's coordinating loading of resources, it's coordinating movement of data. It never stores any data. All machines and data created are kept on the customer side. This is a big thing for security that a lot of customers wanted. They wanted everything to stay in their environment where they can maintain control of it. This gives you that complete control. It also leverages the existing agreement that you have with Ansys. So whatever licenses that you have on Ansys, you will be connecting those licenses to this platform so that you have the ability to access those licenses. So this is merely a coordination, I say merely, but it is a coordination platform to allow you to use your existing commercial agreements with Azure and your existing commercial agreements with Ansys to do more with your simulations. Just a quick note on the products that are covered, the current supported products for Ansys Access on Microsoft Azure. I'm not going to read through this list. You can all scan and see if your product is supported. We support most of our flagship products, and we are adding in on a continual basis. So if you see a product here that is not supported that you'd like to see supported, feel free to reach out to us, post a question in the chat, and we can help answer when that product will be supported. Okay. And then finally, the big advantage that this system delivers is it's the access to the compute power that Azure delivers. And Microsoft Azure currently has, you know, over 500 plus available hardware configurations. Now, that might seem a little daunting when you look at it. How do I make a choice when I have 500? Well, we're gonna, as you'll see from the benchmarks that John is about to show, we've done all the testing. We will tell you which hardware you should choose and how you should use it. The advantage is, as Azure is adding new hardware, you have access to it. You have the ability to take advantage of it, which, if the past is any recent indicator, you will be able to get access to the latest and greatest much sooner than anyone else, and it all possible, which is definitely a big advantage. And then with that, we're going to dive a little bit deeper into the product. I'm going to turn it over to Dr. John Baker, and he's going to cover the solution in a little bit deeper detail than my high-level overview.
Okay, thank you very much, JJ. See if that's, is that coming through?
I'm seeing your screen.
Fantastic. Okay. Sorry. Yep, there we go. Okay, so yeah, thank you very much, and hi everybody. Pleasure to be here today. So I'm going to talk a bit more about the solution. I'm going to talk a bit more about how to use it and what it's all about. So first of all, here's the platform. This is a screenshot in the background showing inside a project space, and you can see that we have 3 resources here. So the first one, we can see an HPC cluster. And this is an auto-scaling cluster. So this is a really, really great way to get access to HPC, because how this works is there's a head node running. So this is a cluster with a head node, but the compute nodes are completely dynamic. So the compute nodes will be non-existent until they're needed. So a job comes in. So you submit a mechanical job into the HPC cluster. The head node will effectively power up the nodes for the job to run on, and the job will solve. And as soon as the job's finished, the data will be saved and the compute nodes will be powered down. So you're getting a really good cost efficiency here, because the compute nodes are only up when they're needed. And you can that means the auto scaling, the cluster auto scales depending on the workload that's coming in. And the head node, you might have persistent, because you need the head node up to make sure that it can receive jobs. You can also power down the head node. So if you're going away, if you're not expecting to run any jobs for a month, you can power down that head node also to save a bit more on costs. The next resource here in the project space is the HPC Platform Services tool. So this is some really cool new technology that we have recently released at Ansys. And this is like a job orchestration layer that we are using as a means to broker, let's say, the engineers who have their simulations that they want to run on HPC with the HPC cluster. So running an HPC cluster is hard. Utilizing an HPC cluster is hard. I mean, we know there's quite a few people who SSH into clusters and batch submit jobs, but it's not everybody's ideal way of running. So that's what HPC Platform Services delivers. It delivers a way for you to submit jobs through a variety of different ways, and then that service will then interact with the HPC cluster. And I'm going to go in a couple of slides' time into a bit more detail about how this technology works, and it's really, really exciting. The next resource we have here is a Windows VDI. So inside this project space, we can create not just an HPC cluster, but we can create desktops as well. So if you wanted to do any pre-post in the cloud, you can do that. And you can take Windows or Linux, depending on application support, and you can run mechanical in these desktops. You can take a GPU if you need it. You can take a high memory machine if you want. You can solve in these desktops if you want. But you may find that getting just a small machine with a GPU is sufficient because you've got an HPC cluster there. So you can prepare your job, and then when it's ready, submit it into HPS, HPC Platform Services, and then let that do the hard work, schedule the job. You can monitor it inside HPS, and off you go. There's lots of flexibility here. So the magic button here inside Ansys Access is this new resource button, and it's highlighted a bit bigger down here. So this is what engineers or IT would use to build out the infrastructure. So if you click on new resource, and you need to have the right permissions to be able to do this, because you can grant which users have access to this button. So as JJ said, you can limit this. So you can have a person who creates the machines and allow just people to connect, or you can let people all have access to this button. So, but they have this button, new resource, and that's how they create machines. So for instance, if you wanted to create a desktop, you can just say, I'd like a new desktop, please. And then you go through a guided wizard. So if you go in the top right screenshot here, we can see the steps involved of how you build out a desktop. And we're highlighting here the application library. So this is what JJ mentioned. This is a library of Ansys applications that are ready to be pulled into your desktops or HPC clusters in a couple of clicks. And these are pre-configured, optimized, tested, validated to just work and work well. And then once you've selected your applications, you then get to pick your hardware. And like JJ said, there's over 500 machine types. We have recommendations based on benchmarking. So we would say, if you're running Fluent, for instance, we would say, hey, you probably want to pick one of these instance types based on our benchmarking, but you are free to pick whichever works for you. If you have a job that you know has a very high memory requirement, needs a very high memory per core, you can pick an instance type that has that right configuration, as long as it's available in your region. So you have so much flexibility here, and the process is very similar if you wanted to create a cluster. We simplify the process of building out this quite complex cluster, but we simplify, we make it easy. You don't need to worry about the Ansys application stack. That is managed by us, and combine that with the Ansys HPC platform services, it's a very streamlined experience. So JJ mentioned the controls we have on the platform. I'm just going to go into it again here. So we have the user controls, which are really important, and these are applied on the project space level. As JJ said, you can have multiple project spaces to divide up the platform between different teams or different projects, and you have that granularity in the controls to really get the environment you want. So like I said, you can give certain users admin, but you may want to give some members just the ability to start and stop and connect. That's all possible. The other nice thing about Ansys Access with the controls is that you can limit where the resources are deployed. So for instance, if you have a team in the UK, an engineering team in the UK, and an engineering team in Germany, for instance, you can have a single Ansys Access deployment and have project spaces connected to each region, but all through the same platform. And this is important if you want to make sure that you can minimize latency, especially if you're running desktop applications. You may want the German side to have desktops in Germany and the UK team to have desktops in the UK. And the project space admin, in this case, can control how that's set up. And then the budget settings. So again, budget settings are on a project space level, and they are really important. You can set a budget limit in each project space. In this case, we've got $1,000. You can set a warning percent. So in this case, it's 80%. So as soon as this project space consumes $800 of machine time, you'll get a nice warning at the top of the page saying, hey, you should probably increase your budget, or just think about maybe wrapping up this project. And once you reach the $1,000, the hard limit, that's the panic button. That's there to prevent any extra cost that you're not expecting to happen, and all the machines will power off in that project space. but all the data stays up. So any file systems you have running, anything that was running at the time, the file systems will remain the same. So you can just top up the budget, power up the machines, and you're in the place where you left it, essentially. And then at the bottom, we're just seeing a summary of what you see when you look at a project space. So you can see the region it's connected to and the current budget level. Okay, so now HPS. So I mentioned HPS is some really cool new technology that we have. If you're familiar with RSM, Remote Solve Manager that we have as a way to distribute jobs to HPC resources, this is just the next generation of that tool. So we have increased flexibility here a lot. And this is ready to go, ready to deploy inside Ansys Access. In your account, you can do this. And we have 3 ways of submitting jobs to HPS. The first is through Python. So if you wanted a really efficient way to work, you can't really get much more efficient than Python. There's no button clicks involved pretty much, maybe one to execute the script. But you can use PyAnsys with PyHPS and run your job, set up your job, run your job, extract the results all through Python. And we have demos coming up for each of these examples in a couple of slides. The other option is through the web portal. So HPS is not just a way for you to submit jobs to the clusters. It's also got a web interface which you can submit jobs through. So you can log into the HPS web interface, upload your model, pick your application, and do it all through a web interface. It has that potential to do, and you can also then monitor your job whilst it's running. So there's a job monitoring functionality inside HPS. So you don't need to SSH to a head node and tail a log. That's no longer required with HPS. You just look at it through a web portal. And for those of you who are familiar with RSM and are using it today and love it, we still have the ability for you to submit jobs through the flagship software in a very similar way, but improved, which I'll mention in a second, in a similar way to RSM through the flagship application. So with that, I'm now going to show a demo of each of those three mechanisms for submitting a job. First, web submission. So this is really nice. So you can submit jobs to a cluster. So here we go. We're going to log into the Ansys Access website. We're going into a project space, and you can see here we have a cluster that's running and an HPS controller. We connect to the HPS controller here, and what this does, this is a connection to the HPS web portal, which is shown here. You can log in with your HPS credentials, which you can set up. There's a few ways to set up authentication. And then you want to submit a job. So we just click Create Project. We give the job a name. We pick the physics, the application we want to use. And these are all installed on the cluster, which have been pulled in through the application library, ready to go. And then you select your input file. So in this case, we're going to pick an MAPDL input file. We can select which results we want to store, which results we want to monitor. And then we've got lots of options. So you can put in your own options here or inherit the defaults. I mean, we're inheriting the defaults here in most cases, except the CPUs. So we're going to change the CPU count to 16. Everything else is just going to inherit the standard template. And then we submit the job. And there it is. So now what's happening is the job is pending. And HPS itself is sending the job to the auto-scaling cluster on the back end and powering up the compute nodes. And you can see once it goes in the running state, you can then monitor the output files and monitor other logs that are running. See here, it's still running. And then once it's complete, we get evaluated up here. And then you can just download the results directly from the portal here. And that next method is from the flagship solver. So this is an example here that was quite tricky to do with RSM, where you had linked systems with dependencies on each other. It involved a lot of data transfer. You'd have to submit these individually, and it wasn't the nicest workflow with RSM, but with HPS is aware of linked systems and dependencies. So here we go into mechanical. We can see our 3 simulations here, modal, harmonic response, and a response spectrum. We set up the HPS queue here in a similar way that if you've used RSM, it's very similar. We put here the HPS server properties. So we log into Ansys Access, we grab the IP of the machine, put it into the URL, test the connection. And I'm just going to pause it here when I say test the connection, because this, with the flagship integrations into HPS, this desktop running mechanical can be both either your local machine, or it could be a machine that you've created inside Ansys Access, so a VDI in the cloud. It's either way works. We've validated both mechanisms. So this could be your local desktop, and you're connecting to HPS up inside Ansys Access for hybrid. So we're just going to test the connection. We validate the user, hit OK. Then we're going to change the cause. So okay, 32 in this example, we pick the HPS, and then we hit solve. So now the job is going from potentially your local machine up into HPS. We can check the job status here, which will take us to the HPS web server. And you can see now the dependencies. It's got all 3 simulations ready, and it's going to run the first modal analysis before proceeding to the next 2. But it's all the data here is staying in the same place. So it's very efficient, much more efficient than it was before. And here we can see, we can monitor the logs as it's going along. We can see the job is running. So cluster nodes have been powered up, it's solving, and you can see it's going through each of these one by one as the dependencies required. Then once job's finished, you can pull the results back to your mechanical desktop, and then again, you can plot things like the frequency response. Okay, and then the last example is the Python workflow. So this is something really nice. So we have an example here of, well, we have just in Windows. Again, this could be on your local machine. It could be in a desktop inside Ansys Access. We've got an input file, an MAPD input file, Python scripts with PyAnsys and PyHPS, and a batch script which ties everything together. What we can do here, so there's the script, we could just drop the text file into the batch script, which calls Python, and you can submit this job simple as this, and it's going to upload the file. It's going to tell you it's uploading the file into HPS. It's going to be in the queue. It's waiting for the compute nodes to power up. It's ready. That's going to go to running. Now your job's running up in Ansys Access, and it's going to download the results for you automatically. And you can see once we back out, we've got the output files here in the folder. So that was super efficient. You just have a Python script, and you don't even have to hit any buttons. You don't have to go to any interface, any web portal. Just submit your results, submit your simulation, download the results. Super simple. Okay. All right. So, and if you want any more information on that, please reach out to us. We'll be happy to give you a live demo of how that all ties together and provide more detail. But now I want to talk about a subject very close to my heart, something I'm very passionate about, and that's benchmarking. So we have single node results to present today. Multi-node will be coming very soon. And I'm going to kick off with Ansys Mechanical. So we have 2 benchmark models here. We have a linear structural analysis on the left. We have a nonlinear on the right. And we have benchmarked 2 of our most frequently recommended instance types here, HBV3, which is an AMD HPC instance type, and an Intel equivalent as well, another HPC machine. And we're looking at the solver rating, which is another word for jobs per day. So the higher, the better. The more solver rating, the better performance you're getting against the number of cores on these machines. And we can see going from I think that's 4 cores to 12 cores, we're getting roughly triple the performance. We're tripling the cores, tripling the performance. So that's often a no-brainer to do. because you're getting perfect scaling. And then from 12 to 36, we still see really good speed up for both of these instance types, and they're both comparable to each other. So for this model, HPV3 or HC44 for a single node run, both are very good options. If we look at the nonlinear example, we can see there's a bit more of a difference here in that HPV3 is a bit more performant than HC44. So we would recommend that you would use HPV3 for this type of analysis. This is a snapshot. This is a picture of our latest round of single node benchmarking between these two instance types. There's a lot of information here. I'm not going to go through it, but please contact us if you'd like to learn more or would like us to look at your models and see what we give some advice on benchmarking. Ansys HPS. So we have some benchmarks here for the mobile phone simulation. If we look at the sub 6 gigahertz frequency range, we've benchmarked the HPV3 again here. So these row 2 and row 3, these are the HPV3. Also the HC44 that was in the last slide is on row 4. We've also included some memory optimized instances, the recommendation of the HFSS team. So these are these E instances here. And we've also included the previous HB generation V2. So this is just another data point, which is quite interesting because we look at the total sim time here. The E64, so the memory optimized instance, is the fastest in this case. HBV3 is very close behind. So in most cases, you can't really go too wrong with HBV3. And if you picked it for this example, then you're not going to be too far off the best performance. What's interesting to point out really is the speed of HBV2. So this is the generation before. And if we compare the 32 core version against the 32 core version of V3, we can see there's quite a big difference here. And that's just from jumping onto new hardware as it's released, which is a massive bonus of the cloud. If you're on V2 and you're taking 1 hour 22, as soon as Azure makes HPV3, in this case, available in your region, you can jump onto that and get this immediate performance gain just by changing a machine type. HPV4 has just been released by Azure, and spoiler alert, there is going to be an HPV4 result on the last slide. But first, the other HFSS benchmark we ran with the same machine types here for the millimeter wave frequency range, and it's a similar story, except that HPV3 comes up on top. So in most cases, you can't go wrong with HPV3. It's a good example. With in this case, 64 cores was the optimal. Still getting good performance when using 32. So the last slide I have is the latest Fluent benchmarks we have. So we looked at the drive air 50 million element model, which is an external aero simulation, and we benchmarked HC44, HPV3, and the latest HPV4 that's very recently made available. And again, we looked at the solver rating or jobs per day against the number of cores. And if we look at the left plot here, this is looking at the performance against the number of cores. And we can see that HPV4, if you look at it core for core, it is the fastest, which is not too surprising. I expected it to be faster. And if we look at around about the 96 core level, you can see that 96 cores of HPV4 here is nearly twice as fast as 96 cores of HPV3, which is quite a significant jump. The other things I want to point out is that you'll see there's quite a lot of plateauing towards the end of these lines, and that's because it's best to run undersubscribed. So in this case, you're not really getting much performance gain going from 96 to 120 cores on this machine. So you probably want to run on either 96 or 64. And it's a similar story with HPV4. But pure performance, HPV4 is going to be the fastest. The next plot here is looking at the impact of hardware cost as well. And this is really interesting. So the higher you are up on this axis is the lower cost your simulation is. And I just want to point out a couple of data points here, and that's around the 96 core point again. And when we look at HPV3, which is the darker line, and HPV4, the lighter gray line, we see these points are very close to each other. So what that is saying is that these two these two virtual machines are costing roughly the same amount to run the same simulation. But the HPV4 instance is roughly twice as fast. So although it costs about the same price to use either HPV3 or HPV4, you'll get your results quicker with HPV4. So, but you may also notice that these lines are very close to each other. So if you can't get HPV4 in your region, HPV3 is a great alternative. And if you can't get HPV3, HC44 is also a good machine as well to choose. But with that, I'll say if any questions on benchmarking, please reach out to us. I love talking about benchmarks. So yeah, and with that, I will hand back to JJ.
Thank you very much, John. Excellently done. And you guys can see that John is very clearly a recovering sysadmin, we'll say, and he loves his benchmarks. So thank you very much for that, John. Let me just share my screen again so I can take over here. All right, is my screen coming through correctly now?
Yep, looking good.
Okay, fantastic. Okay, so everybody, we've got about 13 minutes left here. We're going to wrap up and hopefully have some time for some questions. So if you have questions you've been saving, please look at getting them in. The natural question right now is you've explained the product, you've showed me how it works, gone into details about performance. Now I'd like to try it, okay? As I mentioned before, this is not a product, as much as I know you guys like reaching out to your Ansys account managers and issuing them POs. This is not something that you issue a PO to Ansys for. This is something that you choose the Get It Now option from the Azure Marketplace. So you would go into the Azure Marketplace, and this would have to be an administrator that had the right permissions to do so. You would go into the Azure Marketplace. You would search for Ansys Access on Microsoft Azure, and then you would begin the process to subscribe to this service. As I said, there is no charge for subscribing. The only charge comes in is when you actually use it. What we offer is we offer 1 month of free usage. Now, I need to clarify that month of free usage means that the Ansys charge, that 25 cents that we add to the Azure virtual machine per node, that 25 cents per node per hour, that is not going to be charged in the first 30 days. And that's from when you connect from when you first do your subscription. It will start a 30-day timer and you will not be charged that additional 25 cents. There will, however, be charges for Microsoft Azure. We can work with your Azure teams to get you credits for the actual hardware usage, which is going to be the bulk of the spend that you have. That's the way the system is designed. So the Azure team would need to look at giving you your Azure representatives. Will work with them with you to help get credits, but you will have credits or you will not be charged that 25 cents. So if you are interested in this product, this is how you get it. It is through the Azure Marketplace only. That is the only way to get this product. And from there, you would do the onboarding and set the subscriptions and everything. We did want to profile a success story that we've had with one of our early adopter customers. And this was from a company called Mobilis, who is using Ansys Mechanical and Ansys LS Dyna, and they were looking for a way to run exactly what we've lined out. Their complex critical simulations in the most efficient way in a user-friendly environment. And so they worked with one of our channel partners who they go through to set up the system, and they were able to do exactly that. They were able to take their critical applications, run them efficiently, and in a way, as you saw from the multiple different, I kind of giggled to myself. You know you have a sysadmin whenever he says the Python is the easiest way to do it. But you have multiple different ways, so regardless of the pathway of your users and what they like to use, we can make sure that we're meeting that user-friendly environment, and then we're going to make sure that it's running in the most efficient way. And again, they highlighted in their comment here that we were quick to respond, resolve any issues. This is fully supported by Ansys, so any issues that you have, we will be able to dive into those and help you. We're with you every step of the way. The final thing here, you get to see our lovely pictures there. But this is the contact information for myself and John Baker. I am the global lead, but I have direct responsibility for Americas as well. And John has EMEA. So anybody in, if you're watching this from the APAC region, reach out to me. We have a new hire that'll be on board towards the end of the year, covering that region, but I will be helping you out in the meantime. This is a way for you to, if you scan that QR code, you can book a meeting with us, book a demo, you know, reach out to us and let us know what you're wanting to dive deeper on, whether it's cybersecurity, whether it's you know, end user workflow, any IT configuration questions, things like that. We'd be more than happy to bring in the necessary experts to cover that in a call with you.